Alrighty, gang, welcome back. Today we're going to pick up where we left off last time. So you may recall that we have finished talking about polynomials. Now that we've covered everything with complex roots, the fundamental theorem of algebra, all that good shit, we're done. We're out of polynomial land. Yay! Unfortunately, the next place we're going still has to do with polynomials, although the object of study is something new. So today we're going to be talking about rational functions, which are functions that you build up as ratios of polynomials. Remember, in the same way that the polynomials are like the integer or the function version of integers. Remember we talked about that. Rational functions are like the function version of rational numbers, hence the name. So some things, terminology that you may have heard before that will be relevant here. Asymptotes, remember what those are from any previous algebra classes. Will be playing an important role in this section and the next section. All that stuff to do with multiplicities and local behavior will also be present here. And in addition to talking about local behavior near roots, we'll now also be talking about local behavior near asymptotes. But the rules are very much the same. So strap yourselves in and let's get moving. You may have noticed on WebAssign, I did publish a new homework set for you guys. And that new homework set is 3.6 part 1. So I'm not expecting for us to cover everything we want to talk about regarding rational functions today, which means that you remember our conversation about exam 2 on Tuesday. We said it would either be next Thursday or the following Tuesday. It looks like probably going to be the following Tuesday. It looks like we might need just a teensy bit more time here. And that's okay. This is the stuff that is really important for calculus, is understanding functions and graphs. So we're going to make sure we take the time to get it right. Okay. Here we go. So this is MAC1140, section 008. Which means it's a pre-calc class, and today is the 14th of October, 2021. Today we're talking about rational functions. Specifically, section 3.6. Now, before I dig into this stuff, I do want to share with you guys, I don't think we got to do this on Tuesday. You may have noticed my new background. This new background is something that I've made available to you here, because I don't think we got to look at these in class. This picture is very special. So what the author here has done is they used a computer to generate all possible polynomials with degree no greater than 24 and coefficients either +1 or -1. And then they used a computer to find the roots of all those polynomials. And many of those roots are non-real complex roots, right? So what this picture is the author graphing all of those complex roots in the complex plane. And the picture has a bunch of kind of weird surprises for us. So here's the complex number 1. Here's the number -1. Here's I. And down here would be -I. I can try to load in the full ones. Actually, save somewhere. It's a big photo, 98 megs or something. Anyway, the thing that I wanted to share with you are these kind of weird fractal shapes that show up. Okay. Weird fractal shapes that show up, these feathers. These things look a lot like what are called dragon fractals, and they show up all over the place. The kind of tendency for these polynomials to not want to have roots at 1 or at -1, like right there in the middle of that, there is a colored point there, but you can't see it. It's just this one little point. but it's very, very sparse. Most of the real roots are trying to avoid being at 1. And even the complex roots, you notice all this black space around the number 1, all this black space around the number -1. That's kind of surprising. So something about these like nice numbers, polynomials don't like to have nice roots. They would rather have kind of weird, hard to find roots. And again, this fractal shapes are very, very strange, very, very surprising. It's not something that you would expect to see from any of the normal stuff we learn about polynomials. And if you want to learn more about these, see more versions of these sort of pictures, there's lots of other examples here on this page. Same sort of thing, only this was, I think coefficients here were allowed to run from -5 to 5, and the degrees were a little smaller. But you can fiddle around with these and take a look, and I think you'll find it quite beautiful and quite surprising. And this is one of those places where mathematicians get really excited, because you start to see connections between algebra and geometry, right? The geometry of these fractals, very, very strange. And why would these have anything to do with roots of polynomials? It's not at all obvious. Even if you know how to make fractals like these, and I do, it's usually through something called an iterated function system, it's still very surprising to see them turning up here. It's absolutely beautiful and really, really quite shocking. So there's a bit of a discussion here about why these shapes tend to show up, where they show up, how they relate to polynomials, and the code that's used to generate this is available on GitHub. The link's on the page. I invite you to play with it if you find the stuff at all interesting. Moreover, if you find this interesting, I'd like to let you know that the Santa Fe math team would love to talk to you. So I'm the coach of our competitive math team here at Santa Fe, and the pandemic has been not so kind to us because many competitions have been canceled. But that means that the barrier for entry right now is very, very low. It's super low pressure. We're not doing any competitions right now. It's just kind of a fun environment to talk about whatever sort of cool mathematics you want to talk about. So if you think that stuff is neat, talk to me about the math team. I'd love to have you there. Okay, so what is a rational function? Rational functions are functions which are ratios of polynomials. So the word ratio means fraction. So we're talking about a function, I'll call it r of x, r for rational, and it's going to be of the form p of x over q of x, where p and q are polynomials. All right, so a rational function is what you get when you divide two polynomials. We're going to look at many examples. Of course, every polynomial is a rational function. Just take the denominator to be 1, and you get just the numerator p. So all polynomials are technically rational functions, but most rational functions, we want to look at that denominator being not a constant. And the simplest sort of example there is one of your parent functions. Well, actually, several of your parent functions. But the simplest one is 1 over x. This is a rational function. The numerator, p of x, is the constant function 1, and the denominator, q of x, is the linear polynomial, just x. And some kind of characteristic features of rational functions show up here. So it's a nice example to sort of start playing with. The graph of 1 over x we know, because again, this is one of our parent functions. And these arrows indicate that the function keeps going up, 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 up here forever and ever. And we usually indicate that with a little dotted line. And similarly down here, this arrow indicates that the function keeps going down, 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 down forever. And we indicate that also with this dotted line. That dotted line is called a vertical asymptote. And here I would say that that vertical asymptote is the line x equals 0. Remember, x equals a constant is a vertical line. Y equals a constant is a horizontal line. So this vertical line right here that this function kind of sticks to as it blows up to infinity and negative infinity is called a vertical asymptote. Similarly, the arrows on the left and on the right indicate that the function kind of keeps going with this pattern, getting closer and closer and closer to that line. This is called a horizontal asymptote. And this particular guy is the line y equals 0. Some points that are on this graph. Again, it's one of our parent functions. We should know this graph, but like 1, 1 is right here. -1, -1 is right here. This point would be 2, 1/2. Over here would be -2, -1/2, all sorts of stuff like that. Right? So this is the graph of 1 over x. It has two asymptotes. One is a vertical asymptote, and that's the line x equals 0. The other one is a horizontal asymptote, and that's the line y equals 0. The first thing I'd like to kind of investigate with you guys is where these asymptotes come from. So yeah, where do these asymptotes come from?
Do they come from the x coordinate or like the x point? And the line won't cross over them.
Well, so I'm glad you say that because that's an interesting question that I'd like to address. It is possible to cross over one kind of asymptote, but it's not possible to cross over the other. So it is possible to cross a horizontal asymptote. It's not possible to cross a vertical asymptote, and we'll talk about why. But before we get there, I want to talk kind of about the arithmetic. What is it about this function that creates these things? I heard there was another comment or question.
I thought that asymptotes had to do with like negative exponents.
Sort of, yeah. Vertical asymptotes are, if you're talking about power functions, which this is, right? 1 over x is the same as x to the -1. Those power functions whose power is negative will have vertical asymptotes. That is true. But more than that is true. So at an even more fundamental level, rather than thinking like, what is it about the powers here or the algebra here, I'd like to talk about the arithmetic. And I know that might sound boring, but here's a fact, right? If you take 1 and you divide it by a very big number, then the result will be a very small number. And if you take the number 1 and you divide it by a very small number, then the result will be a very big number. And kind of this is where asymptotes come from. So what's going on here, for example, as x goes off to the right? So if I want to describe this horizontal asymptote, I would say as x gets bigger and bigger and bigger and bigger, the output or y value on this graph is 1 over a very, very, very big number. And 1 over a very, very, very big number is a very, very small number. So as x goes to infinity, 1 over x, this function, I'll just write r of x, goes to 0. All right, when I say big number, I mean like 10 million or something. 1 divided by 10 million is going to be very small, like very, very close to 0. We can do some numerical example if you like. Obviously, 1 divided by 10 is 0.1. 1 divided by 100 is 0.01. 1 divided by 1000 is 0.001. So you see, as I feed in bigger and bigger numbers for x here, 1 over that very, very big number gets very, very close to 0. And that's why this graph is like sneaking up on 0 as we run off to the right. That's where that horizontal asymptote is coming from. And there's nothing special about the big number here. The big number could be positive or negative. As x goes to negative infinity, if I imagine putting huge negative numbers in here, then the output would be a very, very small negative number, right? 1 over a massive negative number is going to be negative because it's positive divided by negative, and it's going to be very, very small in size. So we'd say r is going to 0. And there's a way to indicate the positivity or negativity. So 1 over a very big positive number, if you send x to positive infinity here, dividing 1 by like positive 1 million is going to give you something very, very close to 0, but also positive. And we indicate that by putting a little plus here. On the other hand, as x goes to negative infinity, as we're running far off to the left here, we're putting huge negative numbers in here. The output, this thing, is going to go to 0. It's going to get closer and closer and closer to 0, but it's also going to be negative, and we indicate that by putting a little minus here. So this would be the kind of goes to notation, remember, that we used for end behavior of polynomials, used to describe this horizontal asymptote. And we can use the goes to notation to describe the vertical asymptote also. So the vertical asymptote is coming from the second fact, that if you take 1 and you divide it by a very, very small number, a number that is close to 0, you're going to get a very, very big number. And I can show you some numerical evidence for that. If I take 1 and I divide it by 0.1, I get 10. If I take 1 and I divide it by 100, oh, sorry, other way around. Take 1 and divide it by 0.01, I get 100. If I take 1 and divide it by 0.001, I get 1000. So if you divide the number 1 by a very, very small number, a number very close to 0, you will get a very, very big number. That's why we have a vertical asymptote here. So what's going on with this function? Why is this graph looking like this? Well, as my x values along this graph, this is x equals 1, this is x equals 2, right? As my x values 2, 1, 1/2, as those get closer and closer to 0, the y values are 1 divided by that x value. So for example, right here at x equals 0.1, the y value would be 1 over 0.1, which is like 10, would be way up here. So as these x's get closer and closer to 0, the y values on the graph, which are the outputs from this function, are getting closer and closer and closer to infinity. They're blowing up. They're getting huge. And in that goes to notation, we would say as x goes to 0, my function r of x goes to infinity. There is a little subtlety here. I can approach 0 from the left or from the right. And I'm talking about plugging in small positive numbers. So I would say as x goes to 0 plus, meaning x is a very small positive number, then r of x will be a very large positive number. And on the other side, you have the same sort of thing. If I plug in a very, very small negative number like negative 1/10, then the output from this function would be negative 10, which is like way down here. And in this goes to notation, we say as x goes to 0 minus, if I'm thinking of x as being a very small negative number, then my function r of x is going to go to negative infinity. So the orange here is the arrow notation or goes to notation for asymptotes. So in plain language, a vertical asymptote is a place where your function blows up to infinity or negative infinity. That's all. It's just it's an x value where your function blows up, where the graph of your function explodes. I'll show you here in Desmos. All right, here's 1 over x. And if you zoom out, you see that as my x values get closer and closer and closer to 0, these y values are just exploding. And similarly over here, as x gets closer and closer and closer to 0, the y values are exploding, but now they're going downward because these outputs are negative. So this is the idea. 1 over a big number is a small number, and 1 over a small number is a big number. That's where the asymptotes here come from. Later, we're going to talk about how you find them. There are some pretty straightforward algebra rules for finding asymptotes, but I just wanted to sort of explain to you what they are and where they're coming from. Any questions on this notation or terminology? Okay. So after we're comfy with 1 over x itself, the next step is to sort of look at some transformations of 1 over x. So this is something that you've done before, back when we talked about transformations, but I just want to get a little bit more practice specifically with these guys. Let's sketch r of x equals 1 over x plus 3. R of x equals about x over x plus 2 as transformations. Of y equals 1 over x. The first one is going to be a little easier than the second one. So let's do 1 over x plus 3 first. What transformation do I need to apply to 1 over x to get the graph of 1 over x plus 3?
Would you be able to times it by x plus 3 over 1?
Well,
Or-
remember what transformations we have available, right? We've got horizontal shifts, vertical shifts, horizontal scalings, and vertical scalings. Those are the things we can do.
Would it go up by 3?
If the 3 was on the outside, like 1 over x and then plus 3 over here, that
It
would
goes
be a
on the-
vertical shift.
It goes on the left,
Very good. This is a shift left.
-3.
Yeah, we're going to shift left by 3 units. This pen's not very good. We'll try to make it work. So I take my graph of 1 over x. Asymptotes. At least a couple points, 1, 1. I'll just do these two, -1, -1. And I shift everything to the left by 3 units. So I'll mark off here 1, 2, 3. And I draw in that vertical asymptote. When I shift that whole graph to the left 3 units, the vertical asymptote comes with it. The horizontal asymptote isn't going to move because I'm not moving anything vertically. And then I just draw that same shape, only now it's kind of over here. If I take the point 1, 1 and I drag it to the left 1, 2, 3, that's going to be at -2, 1. And you can see that here. If I take the point -1, -1 and drag it left 1, 2, 3, it's going to be at -4, -1. So this would be my graph. The vertical asymptote is now the line x equals -3. The horizontal asymptote is still the line y equals 0. Any questions on where I'm getting this graph from? This is the first 1 over x. Okay. The other guy, r of x equals x over x plus 2. He doesn't look like a transformation of 1 over x. Not yet. But what you can do to make this look like a transformation of 1 over x is long divide. Or I guess you could do the synthetic division. I'll do the long division. Why not? It's all small enough. So x goes into x once. 1 times x is x. And when I subtract this row from this row, I just get 2. Which means my function can be written as 1 plus 2 over x plus 2. Oh, sorry, 1 plus 2 over x. Yeah, we're dividing by x. And now this is a transformation. This is 2 times 1 over x. That's the 2 over x plus 1. So the transformations here yeah, no, the P's and Q's here are not to do with rational roots then. So here, the 2 is a vertical scaling. We're going to take 1 over x and stretch it vertically by a factor of 2. And then the plus 1 is a vertical shift. So if I want to graph this guy, again, I start with y equals 1 over x. Which looks like this. I'll track those same 2 points, 1, 1, and -1, -1. There are no horizontal things to do here. Remember, we always do horizontal stuff before vertical stuff and scalings before shifts. So the first transformation to apply is that vertical scaling. If I stretch the whole graph vertically by a factor of 2, it's going to look kind of like this. Basically looks the same, right? Just stretched out a little bit. The point 1, 1 is now going to be at 1, 2. So I've stretched everything vertically. And the point -1, -1 is now at -1, -2. Neither asymptotes change with the vertical scaling. So this is not the whole thing, right? This is just y equals 2 times 1 over x. And now if I want to finish things, I need to shift everything up by 1. Which one of my asymptotes will change when I shift everything up by 1?
The horizontal asymptote.
Very good. Yeah, if I take this whole picture and I move everything up 1, then the horizontal asymptote is going to go from y equals 0 up to y equals 1. The point 1, comma 2 is going to go up to 1, comma 3. My vertical asymptote is still x equals 0. And what I have here is something like this for that first branch. If I take the point -1, comma -2, and I move it up 1, that's going to go back to -1, comma -1. And here I would have something like this. So this is my transformed graph. This is the point 1, comma 3. This is the point -1, -1. And the graph here is the graph I wanted, which is 2 times 1 over x plus 1. So sketching rational functions, very basic rational functions as transformations of 1 over x is a nice way to get started. But it's far from the whole picture. Yeah, the +1 here tells me to take everything from this picture and shift it up by 1 unit. So my horizontal asymptote shifts up 1 unit from y equals 0 to y equals 1. My vertical asymptote doesn't change.
I have a question.
Yes.
So for this type of like function, would we only need 2 coordinate points, like if we were graphing it?
I would accept this. It depends on the problem, right? So if a problem is such that it's a little bit tricky to track 3 points or a little bit too time consuming, then I would allow you to track just the 2 points. Kind of like on the inverse function problem from the exam where I said, just give me 2 points on each graph. It's okay. What the big thing is that you track enough points that you can tell what's going on.
Okay.
All right. So way more exciting than graphing these things as transformations of 1 over x is sort of starting to study them in their own right. Let me tell you how to find asymptotes. You notice that the asymptotes kind of form a little skeleton that we can think of like draping our graph on. It kind of gives us a framework. So once you have the vertical asymptotes and horizontal asymptotes, you're in a pretty good position to start trying to draw the graph. Vertical asymptotes, these come from factors of the bottom. And to find them, we set the bottom equal to 0. Now I'm going to give you a procedure for graphing rational functions in general, and you'll see that this is something that comes up pretty naturally in that procedure, because you'll have to factor the bottom and the top at the start. But vertical asymptotes come from places where the bottom is 0. And I'm going to put a tiny little asterisk here, because there is one small caveat. Horizontal asymptotes these follow a 3-case rule. If the degree of the top is strictly less than the degree of the bottom, then the line y equals 0 is the horizontal asymptote. If the degree of the top is bigger than the degree of the bottom, then there is no horizontal asymptote. And if the degree of the top is equal to the degree of the bottom, then the horizontal asymptote is the following line. It's the ratio of lead coefficients. That's your J. So obviously it's this bottom one that's a little bit more complicated than the others. So we're going to take a look at some examples. Thankfully, this rule does always work for rational functions. The vertical asymptote little asterisk there, this asterisk is unless there is a factor shared between the top and the bottom. Which can create holes. Right, so vertical asymptotes come from factors of the bottom unless that factor cancels with a factor upstairs. If that factor cancels with another factor upstairs, then that canceled factor will not create a vertical asymptote. I don't think we're going to see any examples of that today, but that's something we'll look at after you've been able to practice with these sort of simpler examples for a little bit, and we'll see that on for you guys Tuesday of next week. So let's find the asymptotes for a function here, and then see if we can't sketch a little graph. Let's find the asymptotes and sketch the function r of x equals 2x squared minus 4x plus 5 divided by x squared minus 2x plus 1. This is a ratio of polynomials. It's a fraction, and both the top and the bottom are polynomials. Let's start with the vertical asymptotes. How would I find vertical asymptotes?
Set
What
bottom.
maybe just
Yeah, I
Set the
think,
bottom to 0.
right. We want to know where this bottom is 0. Now, rather than stepping aside and setting up that equation, what I would do is let's just factor the bottom, right? We know that polynomials, the places where polynomials are 0 come from the factors. Yeah. So if I factor the bottom, that will tell me where it is 0. So how does that bottom factor? When for two numbers whose product is positive 1.
The x minus 1 squared.
X minus 1.
Yeah, very good. X minus 1 times x minus 1, which is x minus 1 all squared. While we're here, let's try to factor the top. Does the top factor? Remember, we need to watch out for a shared factor between the top and bottom. So if this had a factor of x minus 1, then maybe something weird would happen here. Does this factor? So to get started with my AC method, I'd be looking for two numbers that multiply to positive 10 and add up to negative 4. The divisors of 10 are 10, 5, 2, and 1. I don't see any way to get a negative 4 out of those. And if we want to check to see if this can be factored, we would look at the discriminant, b squared minus 4ac, which is b squared 16 minus 4 times 2 times 5, which is 40, which is definitely negative, right? What is that? Negative 24? Yeah. It's negative. So this is irreducible. Doesn't factor. So the top doesn't factor, doesn't have any real roots. So I know that there's no risk of that thing canceling with something downstairs. So I'll just leave it as it was, 2x squared minus 4x plus 5. So remember, this way to check to see if something a quadratic is irreducible, you compute that part of the quadratic formula, the b squared minus 4ac. That's the part that's under the square root when you're looking for the zeros, the roots. Since that's negative, I know that any roots of this thing would be non-real complex numbers, right? They would involve the number I. So no worries about something canceling. I do see when the bottom is 0, though. When is the bottom 0?
1.
Good. So the vertical asymptote is the vertical line x equals 1. And there's just the one of them. What about horizontal asymptotes? What kind of horizontal asymptote might this have? Which one of these three cases do we fall into?
Would it be the last case?
Very good. Yeah, the degree of the top is 2, and the degree of the bottom is also 2. So the degrees are equal. So that means we need to take the ratio of lead coefficients. What that means is y equals the lead coefficient of the top over the lead coefficient of the bottom. And that's 2 over 1, which is 2. So remember, vertical asymptote's always x equals a constant. Horizontal asymptote's always y equals a constant. Now I want to say a little bit more. I said I want to sketch the graph of this thing, and I'm going to help you get there a little bit this time. What I'm about to do isn't something I would expect you to already know, but I want you to think along with me. So first, let's draw in the asymptotes. I'll mark this as 1. And this as 2. So here's my horizontal asymptote. And here's my vertical asymptote. Now, the fact that the x minus 1 factor downstairs is a multiplicity 2 factor, x minus 1 all squared, there is kind of a local behavior near vertical asymptotes rule that's very similar to the local behavior near roots rule. Let me remind you what 1 over x squared looks like. It looks like this. So if you have a multiplicity 2 factor downstairs, then the vertical asymptote from that factor is going to look like this vertical asymptote, as opposed to like this or this. So you remember that the local behavior near the roots of a polynomial are determined by the multiplicity of the factor from which that root comes. The same thing is true of vertical asymptotes for rational functions. The local behavior near that vertical asymptote is going to be very similar to the kind of basic parent function that has that same multiplicity factor downstairs. In other words, this guy close to 1 looks the same as 1 over x squared close to 0. I'll show you another way to cook this up. I know that my function has to approach this horizontal asymptote and on either side. So there's either going to be an arrow like down here sneaking up on that horizontal asymptote from below, or an arrow up here sneaking up on that horizontal asymptote from above. If I want to know which one is the case, I can look at some other points on the graph. One easy point to look at here would be the y-intercept. If I plug in 0 for x, then this thing gives me 0, 0, 5 over 0, 0, 1. So my y-intercept is the point 0, 5. And because this is up here, it's a reasonable guess that this guy would be approaching from above, because I've got to connect to this piece. And since I have to connect to this piece, I know that I'm going to be approaching this asymptote like that. Because it's an even multiplicity, I know I'm not going to come back down here. I'm going to come back up here, looking like 1 over x squared. And that tells me that I'm going to run off to this side like that. So a good picture of this graph is something like this. Oh, sorry, this should obviously be right here, right? Big ass points. All right, there's the point 0, 5. So this is the graph of this function. It's a little bit tricky filling in all the little arrows before you get started. And so that's going to be the thing I'm going to walk you through gently here. And if you're lucky, you'll have some information from the intercepts to help you out. If you're unlucky, you won't have that information, and you'll have to make a little table. You have to plot a few points. But the truth is, in the worst case scenario, you only ever need to plot 1 point, as long as you remember all the tricks having to do with multiplicity. So let me share with you the fact that we just stated. Local behavior near vertical asymptotes if the factor of the bottom is like x minus c to the 1, or x minus c to the 2, or x minus c to the 3, then the behavior near the asymptote will be like 1 over x near 0, or if it's a multiplicity 2, like 1 over x squared near 0. If it's multiplicity 3, it'll be like 1 over x cubed near 0. Okay, so like a factor of 1 over, like a factor of x minus 3 downstairs tells me that I have a vertical asymptote at x equals 3. If that's a multiplicity 1 factor, then my graph near x equals 3 will look like 1 over x does near 0. In particular, and maybe here's the most important part. In particular, if a VA comes from an odd multiplicity factor, then the rational function r of x will change sign as you go over the asymptote, or at the asymptote at the VA. And if the VA comes from an even multiplicity factor, then r of x will not change sign. So what do I mean by changing sign or not changing sign? I mean going from positive to negative or not, right? So here, this vertical asymptote came from a multiplicity 2 factor. Since 2 is even, I know that I will not change sign, meaning I either go up on both sides or I go down on both sides. Does that make sense? So how did I know we're going up on both sides instead of down on both sides? Well, my y-intercept is the point 0,5, which is positive. If I wanted to get from this point to going down here, I would have to have crossed over the x-axis. But this function doesn't have any x-intercepts because the top is irreducible. So x-intercepts, and I'll write all this out for you in a second, x-intercepts come from places where the top is 0, factors of the top. Since this top is never 0, not for any real numbers, I know that being positive here forces me to be positive here, not negative, because otherwise I would have to cross over the x-axis, but I can't cross over the x-axis because I have no x-intercepts. So this y-intercept tells me that this arrow has to go up. The multiplicity being even tells me that this arrow has to match the first arrow. If this one goes up, this one goes up. If this one goes down, this one goes down. Since this one goes up, this one must also go up. Once I have these two arrows in here, the rest of the graph is easy to sketch. I know then that I'll be approaching this horizontal asymptote from above. And I know then that I'll be approaching this horizontal asymptote from above. Nifty, right? Okay, let's try another example. Actually, let me give you the procedure for graphing rational functions, and then we'll try another example. How about that? So how to graph a rational function. Make sure you get this nice and clear into your notes because most of your homework is based on this. And let me stop for a second and say, as you solve these homework problems, you've heard me say this before, as you solve these homework problems, you must draw the graphs by hand and then match that to the one in Desmos. If you just click through in Desmos till you get the right answer, you're not going to learn a fucking thing. And we saw on this last test how important being able to graph functions by hand is. Right? There were several problems where you had to graph using transformations. And if you didn't practice that back in the transformation section, it really hurt you on this test. I promise you that same shit is going to show up again and again and again in this class, in Calc 1 and in Calc 2 and in Calc 3 and in differential equations. Everywhere through the calc sequence, you need to be able to sketch graphs. All right? Very, very important that you can quickly sketch a graph. So here's the procedure. First, you're going to factor top and bottom. If any factors cancel, make note of that. Second, you're going to find the intercepts. X-intercepts come from setting the top equal to 0. Right, these will come from factors of the top. And all the rules for local behavior near roots that you learned for polynomials apply to rational functions. So if the top has a factor of multiplicity 2, then your graph will bounce off the x-axis like a parabola there. If your top has a factor of multiplicity 1, then your graph will cross the x-axis, just like a polynomial. The y-intercept, this is easy to find. You just plug in x equals 0. And that's true for all functions, by the way, not just rational functions. That's true for polynomials, exponentials, linear, all functions. Next, you need to find vertical asymptotes. And these come from setting the bottom equal to 0, or just by looking at factors of the bottom. And you want to find horizontal asymptotes. Actually, there's only ever one horizontal asymptote for a rational function, and this comes from our 3-case rule. I'm not going to copy that back down. And then you might want to plot a few points. Sketch the local behavior near the VAs and roots, aka x-intercepts. And then connect the pieces. I'm going to come back here and add in just a few little notes. When you're finding your x-intercepts, note the multiplicity. And when you're finding your vertical asymptotes, note the multiplicity. Because these things will help you when you come down here to sketch the local behavior near the VAs and the roots. Okay, are we ready to do this? Any questions about what we're asking for here? All right, let's do it. So let's sketch the rational function r of x equals 2x squared plus 7x minus 4 divided by x squared plus x minus 2. My first step is going to be to factor the top and the bottom. The bottom's easy. Two numbers whose product is -2 and whose sum is +1 is +2 and -1. Factoring the top, you would find two numbers that multiply to -8 and add up to +7. Those are going to be +8 and -1. And then you use your AC method to factor him. He factors as 2x minus 1 times x plus 4. I think we've done that enough that I don't need to walk through the whole AC method thing. So that's the top and bottom factored. There are no factors which cancel. There's no common factor between the top and the bottom. So now I go hunting for my intercepts. The x-intercepts come from setting the top equal to 0. Okay, well, where is the top equal to 0? I have the top factored here, so we don't need to do any separate equation solving. Just tell me, when is this top equal to 0?
½ and -4.
Very good. This factor is 0 at 1/2. This factor is 0 at -4. So this is x equals 1/2, and the multiplicity here is 1, right? Because this is a multiplicity 1 factor. And x equals -4, also multiplicity 1. So those are my two x-intercepts, and because they're both coming from multiplicity 1 factors, the graph is going to cross over the x-axis at those, not balance. My y-intercept, I find this by plugging in x equals 0, and I think it's easier to do that in this original form. So r of 0 is 2 times 0 squared plus 7 times 0 minus 4 divided by 0 squared plus 0 minus 2, which is -4 over -2, which is +2. So my y-intercept is 2. Vertical asymptotes are next. What are my vertical asymptotes here?
½ and -4.
Those are my x-intercepts, right? The x-intercepts come from the top. Where do the vertical asymptotes come from?
-2 and 1.
Yeah, very good. Those come from the bottom, right? Places where the bottom is 0. So that's going to be -2 and +1. And both again are multiplicity 1 factors. Which means that the local behavior near those VAs is going to be the same as the local behavior of 1 over x near 0, right? In other words, near each of those vertical asymptotes, we're going to have something like this going on, or something like this, right? It's not going to be like this or like this. We're going to change sign. One side will go up, the other side will go down. That's what the multiplicity 1 tells me. Okay, horizontal asymptotes, or horizontal asymptote. So there's only ever one of them for rational function. Other functions can have multiple HAs, but not rational functions. What is the horizontal asymptote for this rational function in y?
Would it be 2?
Yeah, very good. It's the line y equals 2. And I'll put a little bit the explanation here. The degree of the top is equal to 2, which is the same as the degree of the bottom. Right? They're both quadratics. So since those degrees match, my HA is the line y equals, and then you take the ratio of lead coefficients. The lead coefficient of the top is 2, the lead coefficient of the bottom is 1. So that's the line y equals 2. All right, now we're on step 5, which is where we actually start drawing the graph. So let me get in here. Everything, place you can see it. All right. Where do I have interesting shit going on? Well, I've got x-intercepts at 1/2 and -4. So I know I need to get all the way over to -4, and I need to use a scale that's big enough so I can see 1/2 also. So -4, -3, -2, -1, 1, 2, 3, something like this. Here's positive 1/2. I have an x-intercept there. And here's -4. I have an x-intercept over there. Moving down my list, my y-intercept is positive 2. There's that. What else is going on? Well, I've got vertical asymptotes, one of them over here at -2. Let's get him in. And we want to label these VA x equals -2. The other VA was at +1. My horizontal asymptote, we said, was +2. Ooh, this is interesting. So this answers a question that was asked earlier. Can a function cross over its horizontal asymptote? Yes. And here it is, right? My horizontal asymptote is this line, y equals 2. But that's also my y-intercept, which means, yeah, this function is going to hit its vertical or its horizontal asymptote. All right, so I've got my intercepts plotted. I've got my asymptotes plotted. I would like to now start drawing in the arrows and the local behavior near these roots. So the first question we should ask, let's come all the way over here to the right. Am I going to have an arrow sneaking up on this asymptote from beneath or sneaking up on this asymptote from above, and why?
Would it be below?
Yes, very good. Why?
Because the x-intercept is there.
Yeah, I know. I was just chilling right down here. So if I'm going to be going from here to getting close to this thing, that means I'm coming up like this, right? So I'll go ahead and draw my little arrow in here. Now, similar sort of logic, if I'm coming over here, that means I've got to cross this guy something like this. It's a multiplicity 1 root, so I know it's going to be a cross, not like a bounce. And since I'm coming in from above, I'm going down below. What we're going to do is work our way left to right across this graph, filling in all the local behaviors. Since I'm leaving here, going down, the next feature I arrive at is this vertical asymptote, and there's two possibilities. Either the arrow goes up here, or the arrow goes down here. Which one do you think is going to happen and why?
It's going to go down.
Yeah, it's got to go down, right? Because I'm leaving here going down. I don't have any other x-intercepts here, so I can't like turn around and go back up. That means I got to be arriving here like this. Okay, as I hop over this vertical asymptote, am I going to come back like this or like this, and why? So I'm negative on the left side of this VA. This VA is coming from an odd multiplicity factor. So am I going to stay negative or am I going to change sign and become positive?
Change sign.
Change sign.
We're going to change sign, right? So because my function is negative just to the left of -2, and this is an odd multiplicity VA, that means I got to come back from above. Now this has to connect to this piece. So I got to cross here something like this, which means I've got to arrive here something like this. And I know I need to cross here because this is a multiplicity 1 root. And now that means I'm coming down here. So I got to show up at this VA like that. And by exactly the same logic, this is also a multiplicity 1 thing. So I'm going to change sign. I came in negative, that means I'm coming back on this side positive. And now that I know coming from here, I'm above, that tells me I have to be approaching this guy like that. So this is your like complete skeleton for the graph, right? In the same way that the end behavior and the local behavior near the roots was our like skeleton for the polynomial graphs, this is that same skeleton for a rational function. You start with your asymptotes and your intercepts, and then you try to figure out the local behavior over here. Once you have that, you can start stitching things together using multiplicities. Very useful, this multiplicity business. If I wanted to draw this graph without using these tricks, I would have to make a big fucking table. I would have to plug in some numbers just to the left of 4 and just to the left of -4 and just to the right of -4 to know that I cross like this. I'd have to plug in some numbers just to the left of -2 and just to the right of -2 to know that I go down on the left and up on the right. And the same thing at every one of these points. I would have to have a table with at least 2, 4, 6, 8, 9 numbers, 9, 10, because also on the left, 10 numbers. I'd have to have a table with 10 rows just to get this information. So Victoria asked an interesting question in chat. Doesn't this interfere with the horizontal asymptote? No. There is no rule that says a function cannot cross its horizontal asymptote. In fact, let me show you some crazy shit here real quick. Anybody taking trig right now? Yeah, all right. So here's an interesting trigonometric function called the sinc function. All right, this is SINC, sinc function. It has a horizontal asymptote of y equals 0, right? As we come out here, this thing is definitely approaching y equals 0. But look at this, it crosses this horizontal asymptote not once, not twice, but infinitely many times. So yeah, you can cross horizontal asymptotes. It's not a problem, not a problem.
In the vertical asymptote?
Yeah, good question, right? So I've been kind of talking my way around that one. Can you cross a vertical asymptote? Is it possible for the graph of a rational function to touch its vertical asymptote? Yes or no, and why?
No.
Correct. Why?
Part of me wants to say because I guess the bottom can't equal 0, but I don't think that has anything to do with it.
No, you nailed it. You absolutely nailed it. Vertical asymptotes come from factors of the bottom, come from places where the bottom is equal to 0. If this function is going to touch its vertical asymptote, that means there's a point somewhere on this VA. But that would mean that you can plug that x value in and get a y value out. But you cannot plug -2 into this function. If you do that, the bottom is 0. The whole thing is undefined. So yes, you can touch your horizontal asymptote. No, you cannot touch your vertical asymptote. Now, this isn't true for all functions. If you let me define a function piecewise, I can sneak my way around that. But for a rational function, a ratio of two polynomials, or any kind of normally defined algebraic function that doesn't involve piecewise funny business, it's impossible to touch a VA. You can touch an HA, you can hit it as many times as you want, but you cannot touch a VA, not without defining the function weirdly. Okay, now that I've got my full skeleton here, I can sketch the graph. And I may modify some of this just a little bit to try and get it to look nice. Like that, right? But this piece is nice and curvy. I just don't have the scale here to show it. If I wanted to show that better, I would do it, you know, like this. Up here, I've got some interesting sort of shape going on, right? I've got something like this. Of course, it continues going up like this. And over here, again, cool little shape going on like this. This one's okay. It's a complicated graph. It is. But we can do it. And it's not that bad. As long as you follow this 5-step process. And the crucial thing to saving time is that multiplicity trick. And you might think, okay, well, I don't want to learn that multiplicity trick here. It's a lot. So I'm just going to make the tables and I'll get through it. The next section on inequalities requires use of those multiplicity tricks, unless, again, you want to waste lots of time. And I promise if you don't learn this multiplicity tricks, you'll run out of time on the test. Okay. Well, that's what we went through there. The question coming in as a DM there was, how do we know the behavior near each of these things? Where did we get those arrows? That was the whole procedure we just went through. So I knew that starting on the left, I knew that this arrow had to be below the HA because I have an x-intercept right here. So I know I'm sneaking up from below. I'm not coming in from above. I'm down here. So if I'm going to come in from down here, that means I've got to do something like this. And that means we're crossing here like this, which means I'm coming down here, which tells me this arrow goes down. Then because this vertical asymptote was an odd multiplicity, odd multiplicity thing, I know that it's going to be down on one side and up on the other. So once I know it's down on the left, I know it's up on the right. So then I've got my little arrow here going up on the right. That tells me my graph is going to come, you know, down like this. And I've got an x-intercept over here, a y-intercept right here. So I've got to come something like this, which means I'm going to be approaching this vertical asymptote going down. And again, this vertical asymptote came from an odd multiplicity factor. So if I'm going down on the left, I've got to be going up on the right. That gave me this arrow. And that arrow tells me that I've got to be approaching this asymptote from above. I've got to be coming in like this, not like this, because I can't, you know, I don't go down here. Yeah, all of it comes from the multiplicities of the factors of the top and the bottom. Now, it is possible that you get into trouble if you don't have any x-intercepts, because then you don't have any way to kind of get started over here, right? Like I got this arrow from this x-intercept, and in that case, you might want to plug in 1 or 2 numbers, make a very small table. But you don't want to waste time making a table with 8, 10, 12 points in it, because you're gonna run out of time on the test. And we want to be able to do this shit quickly. Okay. I think we are just about out of time here for today. So please take a look at that homework set that is up for you now. There's a homework, and there's several homeworks that are still open because I gave you extra time on those polynomial homeworks. There's the new homework for rational functions, and there's also a quiz that I want you guys to be working on between now and next Tuesday. Remember, the test 2 is getting quite close. Not next Thursday, because I think we're going to spend an extra day on the rational function stuff, but the Tuesday after. So there's going to be, between now and the test, there's going to be 2 more homeworks, right? There's going to be a part 2 to homework 3.6, and then there's going to be homework 3.7. And there's going to be another quiz. So between now and the test, you're going to have 2 more homeworks and a quiz, in addition to the stuff that's already there. I'd like everybody to be caught up by next Tuesday. So if you're struggling with something, please come see me in office hours, talk to me in Canvas or Discord or somewhere, and let's get ourselves caught up and ready for this test. Next time we meet, we're going to do a little more practice with this sort of stuff, just like this. And then we're also going to start looking at rational functions where there might be a hole in the graph or other kind of weird things that can happen. And then we're going to start talking about inequalities, so how to solve inequalities involving these functions. It's sneaky, it's fun, but it's not impossible. It's far from impossible. I promise you guys you can do it. But you need to practice. You need to practice and do so honestly and independently. Don't use cheaty software, and definitely don't just click around on Desmos till you get the right answer. Take the time, draw the graphs, and if something doesn't match, try to figure out why. If you can't figure out why, talk to me, talk to a tutor, talk to a classmate. But don't let those things just sit. Definitely put the time in to try and understand it. Before I let you go, let's take a look at this thing in Desmos and see how we did. This function's wild, isn't it? I love this thing. We called our function r of x, and it was 2x squared plus 7x minus 4, all divided by x squared plus x minus 2. And let me set my scales back to something normal. There we go. So compared to this, not bad, right? I can draw in my asymptotes. And yeah, looks just like my graph, right? Compare. Got this branch on the left. Got this branch on the left. Got this S curvy thing in the middle. Got this S curvy thing in the middle. We've got this branch on the right. And this branch on the right. Our x-intercept, positive 1/2 and -4. And the y-intercept, positive 2, crossing over its horizontal asymptote right there. All right, that's it for today. Next time, more practice graphing rational functions, and then we're going to move on to dealing with rational inequalities. So solving inequalities involving these things. Again, please practice. If you're having a hard time with anything, please ask for help. I'm here to help you. Remember, test 2 is not that far away. All right, I'll see you guys next time.